Hello. We covered in previous lecture the introduction of diffraction and two classes of diffraction, namely Fresnel diffraction and Fraunhofer diffraction. In this lecture, our focus will be on Fraunhofer diffraction at single slit. In this, we have a plane incident wavefront WW dash, a single slit AB of width E, a lens L2 placed adjacent to the slit, and a screen placed at second focal plane of the lens. The diffraction of light takes place at the single slit here, and the diffracted light is focused on screen to give diffraction pattern. We need to know the intensity profile at the screen. In other words, we wish to know the intensity at an arbitrary point P1 at screen where all the diffracted waves at an angle theta with respect to direction of initial light ray get focused using lens L2. Angle between P1O and P0O is theta. This angle theta is known as angle of diffraction. Let us talk about single slit alone and diffracted light. As a methodology, we will divide the slit of width E into large number of equal segments which act as secondary sources emitting secondary waves. These secondary waves travel in all the directions and meet at a point on the screen depending upon the angle of diffraction, and they will interfere there. All the parallel diffracted light rays traveling in diffraction angle theta with respect to the original wave meet at a single point at the focal plane of the lens. For a start, choose an angle of diffraction theta, find the path difference between consecutive light rays, and then find the resultant amplitude at the screen, and then generalize the result. So, this is the single slit AB. The width of this slit is E. This is the direction of original wave. First, divide the slit into n number of segments. N is a very large number. The rays 1, 2, 3, 4, 5 and so on up to n will emit as the secondary wavelets from all the segments. Since all the segments are identical, so the amplitude of all the secondary waves will be the same. Let this is A. To find the phase difference between consecutive light rays, let us first find the same between first light ray and the last nth light ray, and then we will divide this phase difference by n to find the phase difference between any two consecutive light rays. Let us draw a perpendicular from point A on last light ray, and BC will be the path difference between first and last light ray. Angle BAC will be angle theta equal to theta. Now the path difference between ray number 1 and ray number n will be E sin theta. Corresponding phase difference is 2 pi E sin theta by lambda. Then the phase difference between any two consecutive waves from these different parts will be this part phase difference divided by n. So let this phase difference is denoted by delta, then delta will be equal to 1 by n times 2 pi E sin theta divided by lambda. So the phase difference between any consecutive light rays, this delta. The phase difference between first and third light ray is 2 delta. The phase difference between first and fourth light ray is 3 delta. The same between first and fifth light ray will be 4 delta, and so on. So there are n equal amplitude light rays with increasing phase difference with respect to the first, and they are traveling in the same direction. They will give a resultant amplitude R at the point where they will meet. So The problem is reduced to finding the resultant of n equal magnitude vectors with path difference between consecutive vectors equal to delta, where delta is given by 2 pi e sin theta divided by n lambda. So to find this resultant, we use the polygon method of vector addition. Here, let this vector is the first vector corresponding to the displacement by the first secondary light ray. This is the second vector corresponding to the second secondary light ray. The angle between this vector and this vector is theta. This is third vector, this is fourth vector, and so on. And the resultant vector is mpn. So this will be the resultant at the screen. We need to find the length or amplitude of this resultant vector. The length is r theta. So to find r theta, let us draw normal bisectors of all the vectors. So this is normal bisector on first vector. The angle between all the bisectors will be the same as the angle between consecutive vectors. Angle MCX will be delta by 2, and this angle will also be delta by 2. In triangle MCX, this length is half of the length of the vector, and MP1 is A, so MX will be A by 2. And this length is MC. Because this angle is delta by 2, so we can write sine delta by 2 is equal to mx divided by mc, as this angle is 90 degree. And by this we can find mx. Mx is mc multiplied by sine of delta by 2. Mx is a by 2, so this equation becomes a by 2 is equal to mc sine delta by 2. We have another triangle. We draw a normal bisector on MPN, and this bisector is CY. This whole angle is n delta, and angle MCY will be n delta by 2. Again, the length MY is r theta by 2. And so sine of n delta by 2 will be equal to my divided by mc here, and this gives my equal to mc sine n delta by 2, and my is r theta by 2, so this gives you r theta by 2 equal to mc sine n delta by 2. So we have these two equations. So by dividing one by other, this gives r theta by 2 upon a by 2 equal to sine n delta by 2 divided by sine delta by 2, or r theta is equal to a sine n delta by 2 divided by sine delta by 2, or this is the resultant r theta. So next, the resultant r theta at any point on the screen is this, or this is equal to a sine n delta by 2 divided by sine delta by 2, where delta is 2 pi sine theta by n lambda, or it can be written as r theta equal to a sine alpha upon sine alpha by n, where alpha is pi e sine theta divided by lambda. This is another parameter we have used to reduce the size of the equation. Because this n is a very large number, so alpha by n will be very small quantity, and so sine alpha by n can be written as alpha by n. So this equation becomes r theta equal to n a sine alpha by alpha. This a is the amplitude of one secondary wave, and this na will be the amplitude of the incident wave. Suppose that is a naught. So the resultant at the screen will be r theta equal to a naught sine alpha by alpha. The intensity is the square of amplitude. So intensity at the screen will be I equal to I naught sine alpha by alpha's whole square. So and alpha is pi e sine theta by delta. So as theta increases, alpha also increases. For theta equal to 0, alpha is equal to 0. Now we find the intensity distribution on the screen, where we have already I equal to I naught sine alpha upon alpha whole square as the intensity. So to find the intensity profile, we see that this intensity depends upon alpha. So to find the minima or maxima, differentiate it. This differentiation gives alpha sine alpha multiplied by alpha cos alpha minus sine alpha equal to 0. So this is possible if either alpha equal to 0 or sine alpha equal to 0 or alpha cos alpha minus sine alpha equal to 0. So we choose these two conditions. The case 1, sine alpha equal to 0 gives alpha equal to plus minus m pi, where m is any natural number including 0. So at m equal to 0, alpha is 0, and this gives sine alpha upon alpha when alpha is very less, alpha tends to 0, is equal to 1. So the intensity will be maximum, and that will be equal to the incident intensity. This condition is known as principal maxima, and this corresponds to theta equal to 0 without diffraction. M equal to non-zero numbers, m equal to plus minus 1, plus minus 2, plus minus 3, give another values of sine alpha which all are equal to 0. So these are corresponding to the minimas. So these are minimas. So m equal to 1, 2, 3, or e sine theta m equal to plus minus m lambda is the condition for minimas. So this is alpha equal to 0 gives the principal maxima, alpha equal to m pi gives minimas, and condition alpha cos alpha minus sine alpha equal to 0. This can be reduced to tan alpha equal to alpha. This is the condition of secondary maxima. This condition tan alpha equal to alpha cannot be solved analytically. So to find the solutions, we have only numerical solution method. The solution of the equation tan alpha equal to alpha is given by the intersection points of these two equations, tan alpha equal to y and alpha equal to y. So we draw both the equations on a single graph. X-axis denotes alpha and y-axis denotes y. So this is y equal to alpha, and y equal to tan alpha are these graphs. This one, this, and these. So the intersection points are at origin, and these also. This solution corresponds to the principal maxima. So this is not a secondary maxima. So our solutions are this 3 pi by 2, this around 5 pi by 2. So these are the approximate solutions. The exact solutions are alpha equal to 1.43 pi, 2.46 pi, 3.47 pi, and so on. So the approximate solution can be written as alpha equal to m plus half pi, where m is 1, 2, 3, 4, and so on. M equal to 0 is not a solution at all. This solution reduced to e sin theta m equal to plus minus m plus half lambda, where m is 1, 2, 3, 4, etc. and theta m is angle of diffraction for secondary maxima. Since principal maxima comes at the points where alpha equal to 0, and we know that sine alpha upon alpha for alpha equal to 0 is equal to 1, So the intensity of principal maxima is I naught. The intensity of secondary maxima can be found by placing alpha as 3 pi by 2, 5 pi by 2, 7 pi by 2, etc. So we see that the ratios of the intensities reduce very fast. So the highest intensity is of principal maxima, and then the intensity of secondary maxima is very less when compared to the intensity of principal maxima. So this is the profile of intensity at the screen due to single slit. So this principal maxima is very bright. Then you will get the minimas, and then secondary maximas have a little intensity. We can find the fringe width at the screen also, as we know already that for the principal maxima alpha should be equal to 0, and for minimas alpha should be equal to n pi. Alpha equal to pi for first minima, alpha equal to 2 pi for second minima, and so on. And secondary maximas have alpha equal to n plus half pi, means first secondary maxima corresponds to alpha equal to 3 by 2 pi, then for second alpha equal to 5 by 2 pi, and so on. So we have condition for minima E sin theta equal to m lambda, where m is a natural number. For secondary maxima, this E sin theta should be equal to m plus half lambda. Here we know that this focal length is very large. So we know that tan theta is equal to z divided by f, and z is very less, f is very high. So this theta should be very less. So tan theta can be written as theta. Further, the condition for minima can be written as E sin theta equal to E theta, because theta is very less, equal to m lambda. If we put the value of theta z by f here, we can find the conditions. For mth minima, z minima will be m f lambda by E, and for maxima, the same will be m plus half f lambda by E. So we can find the positions of maximas and minimas. So these are the positions. Z for minima will be f lambda by E, 2f lambda by E, 3f lambda by E, and so on. And the positions of maxima will be 3f lambda by 2e, 5f lambda by 2e, 7f lambda by 2e, and so on. We can have some facts about single slit diffraction. We have the condition for minima, that is E sin theta equal to m lambda. Sin theta cannot be greater than 1, and m cannot be less than 1. So this is clear that E should be always greater than lambda, and this is the essential condition for diffraction, and that is the finite width of the slit. Finite width means greater than lambda. So if E is infinitesimally small, diffraction is not possible. Now the distance of mth minima from the center is z minima equal to mf lambda by E. So here known is the focal length of the lens and width of the slit. The measurable is z only. Z is the half width of the principal maxima. So in this equation we can have the lambda calculated by these values, and this is all about the single slit diffraction.